helicopter performing aerobatic maneuvers. So this is manually flown, and so this we have this same size, same class of helicopter in our lab also. So its rotor diameter is about 1.5 meters, and this is capable of doing extreme aerobatic maneuvers. So let's take a look at this video, and you can see that it's capable of attaining all altitudes, and also it's capable of performing high angular rate turns, and it can also do inverted flight because the thrust can be inverted. It can generate negative thrust also. So this kind of maneuver is possible for this size of helicopter because of the way the rotor is designed. So it is very important to study the way the rotor is designed and how this class of helicopter is different from other large scale helicopters, which won't be able to perform this kind of maneuvers. And it's also very precise in the sense that you can have like very accurate movement of this helicopter coming out of the control input. So that was just the motivation for studying the rotor dynamics or looking into the rotor dynamics. Inertial force. Okay, now I am going to do it for centrifugal and the remaining forces and the spring moment. Omega square r minus e into dr into beta minus e to r fz into r minus e into dr plus k beta into beta, and that should be equal to 0. Okay. So this integration is along the length of the blade, so it is independent of beta. So I can perform this integration, and I'm sorry, there is one r minus e into dr is the force, and then there is the moment, this thing. So I forgot to put that. I'm putting it there. So I'm going to, so what is this term? Just this integral, integral e to r m r minus e square dr. So this is the moment of inertia of the blade about this axis, which is coming out of the board and passing through O, is it not? Okay. So I am going to call it as I beta. Okay, and so you can write the second term, actually this whole integral, as you can write this r as r minus e plus e, and after simplification you will get something like so you can write it as integral e to r m into r minus e, actually let me just write it down here. So I am just going to take this integral and I am going to write it down here. Integral e to r m into omega let me not be worried about this omega because it's constant, r minus e whole square into dr plus integral e to r m e r minus e into dr. Okay. So if you simplify this, you will get I beta into 1 plus integral e to r e m into r minus e dr by I beta and this term for this particular assumption that we have a rigid blade flapping, this term reduces to 3 by 2r. This is 3 by 2r. Okay. So so after making these substitutions like I beta and then I beta into 1 plus 3 by 2r, this whole equation reduces to this form. So you have this I beta times beta double dot plus omega square into 1 plus 3 by 2r plus a beta by I beta, this whole times of beta, that is equal to integral e to r fz into r minus c into dr. Okay. So this is a second order equation in beta. Okay. And where is the control input appearing? Because there is no control input happening anywhere on the left hand side, but you have this Fz term, which is this aerodynamic force at that elemental location, which is integrated from here to here, and that is where the control input is hiding, and it has not yet come out. So the idea is to reduce this equation further so that you can explicitly see the control input in this equation. So for that we will write, we will do a change of, the independent variable is changed from time to the azimuthal angle psi, because they are both related. So you have this d psi by dt, or in other words you can just say that the rotor is rotating at a constant speed, this blade. So you can say that we can write psi as, without loss of generality, omega into t, where omega is the angular velocity of the rotor. Okay. So you have this relation d psi by dt is omega, and if you write everything in terms of psi, this equation further reduces. In that, of course, you can write beta as a function of psi, which is a function of time. Therefore, you can write d beta by dt as d beta by d psi and d psi by dt, which is omega. Okay. And d square psi by dt square is 0 because omega is constant. So d square beta by dt square is omega square times of d square beta by d psi square. Okay. And this is denoted as double dot, and I am going to denote d square beta by d psi square as beta double prime. Okay. All the derivatives with respect to psi will be denoted as primes. Okay. So if you make this change of independent variable, then this equation changes to changes to beta double prime. Now everything is written with respect to, so all the derivatives are taken with respect to psi, and after substituting these relations, we have beta double prime plus nu beta square times of beta, that is equal to 1 by omega beta I beta into omega square into integral e to r fz dr into r minus c. So the right hand side is as it is. Now we have a new term coming in, it's just nu beta and is equal to this term, non-dimensionalized. So that is 1 plus 3 by 2r plus omega beta naught by omega square whole thing power 1 by 2. And this is called the non-dimensional rotating natural frequency. Okay, and this is a very important design parameter for helicopters. And omega beta naught is given by actually omega beta naught square is given, or in other words you could just write this as k beta by I beta, and this is the non-rotating. So the previous one was rotating natural frequency, this is the non-rotating natural frequency of the blade. Okay. So so what can we infer from this equation? So this is a second order ODE, and what it says is that so there is a this can be compared with your regular spring mass damper system. So you have your mx double dot plus cx dot plus kx is equal to some forcing function f of t. So here you have your regular spring mass damper system, and of course it can also be written as x dot plus 2 zeta omega n x dot plus omega n square into x is equal to sum f by m normalized force. Okay. So if I have a forcing function which is at the natural frequency, then I will see that, I mean, if there is no damping in the system, then I will have okay, let me put it this way. So let me draw the diagram for the frequency ratio versus the phase relation for the input forcing function and the response. So if I have my omega by omega n, and I am drawing this for this, okay, for the spring mass damper system, and here is my phase angle. By phase angle I mean it's the phase angle, phase difference between the input forcing function and the response. So the response is x of t and the input is f of t. So let's say that f of t is periodic, then you will have a periodic x of t. The frequencies are going to be the same, but it's going to be phase shifted, and also the amplitudes are going to be different because this is a linear system. So for different damping ratios, that means for different xi, we will have something like this kind of a phase relation. So this is my pi, and this is pi by 2, and this is 0. Okay. So when I have my omega by omega 1 S1, so when I force my system at the natural frequency, then for different damping ratios, this is the phase relation that I have. This is 1, So this is for xi equal to 1.0 critically damped system, and this is for under damped system. I mean these two. So what it shows is that if I have my natural the forcing forcing frequency matching the natural frequency of the system, I will have an exact so essentially if I try to resonate the system now, because I have this some kind of damping, viscous damping in the system, it will not blow up, the system will not blow up. But what it says about the relation between the phasing of the relation between the phase between the input forcing function and the response is that if I exactly have omega equal to omega n, then I will see a 90-degree phase shift between the response and the input. So a similar similar thing is observed in this differential equation also. Of course, you may be wondering where is the damping in the system. So the damping in the system is lying within this fz. So fz is also a function of the beta dash. So it is there inside this. And what is interesting is that because we have this swash plate mechanism, I guess you have already seen the swash plate mechanism in your previous class. The forcing is always at the frequency at the angular velocity of this blade. So the forcing happens at omega. Okay, this is how the forcing is happening. Now the question is, what is the relation of this forcing frequency to the natural frequency of the system? So the natural frequency of the system is nu beta times omega, because nu beta is non-dimensional rotating natural frequency. If you want to give it the right dimension, then you have to multiply it with this omega. Okay. So for the helicopters that we have in our lab, nu beta is more than 1, but it's not so high. I mean, the sense that it will be something like nu beta will be of the order of 1.075 or something. Okay, so it's very close to, so nu beta is nothing but the forcing frequency to the natural frequency to the forcing frequency. Okay, so this is like omega n by omega. So my omega by omega n would be less than 1 but very close to 1. So it would be something like over here. So what it shows is that my helicopter, if I have the maximum force on the blade at this location, I will see that the blade flaps maximum, I get the maximum blade flapping at close to being 90 degree, but a little less than 90 degree. And that, where exactly it happens, comes from this number nu beta. And you can see that this nu beta is a function of E. So this is this hinge offset, okay, and it is also a function of omega beta naught. Omega beta naught is the ratio of this root stiffness to the blade inertia, the moment of inertia of the blade, and it's also a function of the rotating frequency of the blade. So if you have a very large omega, so it's closer, the nu beta would be closer to 1, or in other words, if you have, let's say that you have E 0, so your hinge is exactly at the rotating axis, and if there is no spring associated with the this blade, so there is no spring over here, there is no torsional spring. In that case, you have your nu beta exactly equal to 1, and at that so for that particular rotor system, your response would be exactly at 90 degree, not somewhere here. Okay, so this is interesting because when you consider tracking problems for helicopters, you need to have like you need to know where exactly your maximum deflection is happening of the rotor. Otherwise, there will be some amount of tracking error. For stabilization, this for attitude stabilization problems, this phase shift will not cause much of a problem. But you should always know that the point where the blade is subjected to maximum force and the point where you get the maximum deflection, it is off by almost 90 degree. If you don't take into account this part, then your system will not, you cannot even stabilize your system. So that's about the rotor design. So these are the parameters that one can play around with, and you can look at the phase shift associated with the blade. So why did we consider this kind of model? Because the helicopter that we have in our lab, it does not have this kind of an arrangement. What we have is a hingeless blade system. So there is a way to approximate a hingeless blade system to this kind of a standard model. So how do we do that? So what we have is a hingeless system. Hingeless blade with equivalent hinge offset. So in case of a hingeless system, we have, once again, this is my ZH, and the blade would, so there is no like clear distinction where is the hinge offset and where is the spring and other things. So you have a continuous deflection of the blade. So this is my blade here, bending like this, and there is no, so the complete stiffness of the blade is responsible for this equivalent stiffness k beta. So how do we get these parameters E and k beta from a given hingeless system? So there are two ways to obtain E and k beta. One is to compare the rotating and non-rotating natural frequencies of the two systems. So you can write mu beta as omega beta by omega, and that is given by this equation relation that you have, 3 by 2r plus omega beta naught by omega square power 1 by 2, and then k beta is given as omega beta naught square times of I beta. Omega beta naught is the non-rotating natural frequency, and this can be measured by tapping the blade, and you can measure the frequency of the natural frequency of this blade. So this is measurable, and I beta is your moment of inertia about this axis, that can also be measured, and from that you can obtain k beta. And once you have k beta, you can get E just by inverting this relation. So that's 2 by 3 r times of mu beta square minus omega beta naught minus 1. Okay, and here we are assuming that we are able to measure this rotating natural frequency also. I guess there is a way to measure the rotating natural frequency by some kind of instrumentation. So if you know this rotating natural frequency, and if you know the non-rotating natural frequency, this is easy to measure, this is hard to measure. So if you know these two frequencies, there is a way to obtain k beta and E. This is one way of obtaining k beta and E. Another way of doing it is by studying the bending of this blade when you give a static input to this blade.
Omega beta naught is easy to get, right?
Yeah, yeah.
And we know capital omega, right?
We know capital omega.
So then directly we can get VB or whatever you are calling that.
No, no, no. See, this is omega beta. This is omega beta. They are different objects. Omega beta is your rotating natural frequency. Omega beta naught is your non-rotating natural frequency. So if you non-dimensionalize your rotating natural frequency, you get nu beta. Okay. So the second method is by studying the bending of this blade when you subject it to a steady static load. So what we do is that we look at 75% of this rotor length. So I will look at 0.75 times of this rotor length. Rotor length is denoted by capital R. I will take this point, and from this point I will draw the slope of this, I will draw a tangent to this blade. Okay. It will go and intersect this axis at some distance, and this whole thing is my E. Okay. And once you have your E, so this can be easily expressed as, let's say this, the slope is given by dou, let's say the deflection is like this is my W tip, this is my maximum deflection at the tip, and then E would be given as R minus W tip by dW by dr evaluated at 0.75 R. Okay. Okay. And your k beta is obtained as okay, I should have written it like here. I'm sorry about that. Now your k beta is given as I beta omega square nu beta square minus 1 minus 3 by 2R. Okay. So this is the other way of obtaining these values. So we have this equation of motion, but we still don't have, so let's move on. We have this equation of motion and we still don't have our control input anywhere. Now we are going to obtain the control input by doing some simplifications. So this part will be the rotor tip path plane equations. So tip path plane would be denoted by TPP from now on. Equations. So we know that the forcing function is a 2 pi periodic function, and hence the response is also going to be 2 pi periodic. Now we can approximate this beta along the azimuth as a Fourier series expansion. So you can write your beta as so the general solution to your beta would be you can expand it like this. So these are the coefficients beta naught, beta 1 c, beta 1 s. Okay. But we are primarily interested in the first harmonic response of the rotor. So we will not be considering the remaining terms of this Fourier expansion. So we will say that, and we are also interested in the time evolution of the beta 1c and beta 1s. So what are these coefficients beta naught, beta 1c and beta 1s physically? So what happens is that you have the rotor, and if you just write the beta as a function of psi and just include these three terms and ignore the remaining terms, the shape of the rotor as a result of the control input would look something like this. So it would look like a cone. Okay. Okay. So this is my thrust vector. So this is how my rotor disc is going to, so this is the tip of the rotor and this is like the blade, and when the blade rotates like this, so you have this conical region, and this is the tip of the blade and it will be traversing like this. So this makes a cone, and this plane is known as the tip path plane. Okay. And we can describe the orientation of this cone with respect to the hub plane. In terms of three angles, and this is my z edge, the hub vertical direction, and this can be described by three angles. One is your beta naught, which is the coning angle of the rotor, and the orientation of this cone can be described by two angles. One is along the x axis, I guess this is my y axis, x axis, and here I have my helicopter. This is the top view. So the tilt of this cone about this x axis, so if I measure it from the y axis, it would be beta 1 s, okay, the tilt, and here I will have my beta 1 c. Okay. So this could be beta 1 s or beta 1 c depending upon where I am measuring this angle from. Okay. So if I just write it in terms of these angles, ignoring the remaining terms, I would get so I am also interested in the time evolution of this tilting of the rotor disc, okay, not just the steady state values. So I am going to parameterize these slightly differently. The coefficients are now a function of my function of time. So you can put a t also here, is beta naught of t minus beta 1 c of t cos psi, that is beta 1 s of t into sin psi. Okay. So if you substitute this equation, this relation of beta into this equation, then you will have, and of course you need to write your fz as a function of angular velocity of your fuselage and the flap angle and their the rate of change of flap angle, and you expand all these things, then you will eventually get a second order equation in terms of these three beta naught, beta 1 c, beta 1 s. So this is obtained by comparing the coefficients of cos, sine and the constant terms. Okay. So it comes out to be of this form: a double dot plus d a dot plus k a is your f. F is the forcing, and what is a? A is your beta naught, beta 1 c, beta 1 s. Okay. And I am going to denote, rather than using beta naught, beta 1 c, beta 1 s, I am just going to call them as a naught, a and b. Okay, this is just renaming, because this convention, so this convention is used when you look at helicopter dynamics textbooks and all, but this convention is used by small scale helicopter community. So I am going to stick to this because our helicopter that we considered for controller development and other things, we have used this convention. And your D and K are the, so D is the damping matrix and K is the stiffness matrix and F is the forcing term. So if you want to know what these terms are, you have to look into the one paper, NASA technical report by Chen. So that it's called Effects of Primary Rotor Parameters on Flapping Dynamics. Okay. So this equation, so this is a collection of 3 second order ODEs. Now this will have 3 modes, and so the 3 modes associated with this equation are so first you have your coning mode. And then you have the advancing mode. They are just the names given to each mode. And then you have the regressing mode. So the corresponding to these modes, so coning mode is so if you give the collective input to the helicopter, so the rotor actually cones like this, and the frequency associated with that coning is nu beta. This is the natural frequency associated with the coning mode. And for the advancing mode, you have the natural frequency is nu beta plus 1, and for the regressing mode you have nu beta minus 1. So these are the natural frequencies associated with these modes. And nu beta is approximately of the order of your angular velocity of the rotor. So that is omega. So this is approximately of the order of omega, and this would be approximately of the order of twice of omega, right? Because this is nu beta is approximately 1, 1 plus 1 is 2, and 2 times, if you non-dimensionalize it, it's twice of omega. And this is something very low value, and this is the mode that is going to interact with your fuselage dynamics. Okay. So the advancing mode, what is it is kind of like a nutation of the nutation mode that you will find in a rotating rigid body, and your regressing mode is like precession, and this turns out to be very slow in the sense that if my omega nu beta, which I have previously said it is like 0.075 or something, and if you take this difference 0.75, I mean 0.75, you multiply it with omega, which is 25 or something, you will have something of the order of 1 point some hertz. and this is this frequency is the one which is going to interact with your fuselage dynamics, because the fuselage is also, it's something that you are trying to control, right? We are trying to control the orientation of the fuselage by using your rotor. So we are primarily interested in studying the regressing mode, because the remaining modes are, there is no point trying to control these modes because they are pretty fast. So in order to just get the regressing mode, we can just so this is a collection of 3 ODEs. We can just do away with the coning mode. So just abandoning this coning mode would mean that you just don't take the first equation. So just forget about A naught. And so if you want to remove the advancing mode, the way it is done is by so this is a second order equation. You just don't take A double dot and terms containing angular accelerations. Okay, so this is described in small scale system identifications for small scale helicopters by Mettler. You can look up. So ultimately we are left with a first order differential equation. So for so once you neglect the coning mode, so you are left with this 2 by 2 matrices for D, K, and F is a 2 by 1 vector. So your D would be omega times of gamma by 2, 2 minus 2. I think it's not gamma by 2, it's gamma by 8. Okay, and your capital K is omega square small k beta by I beta omega square gamma by 8 minus gamma by 8 k beta by beta omega square, and your forcing will have terms like it's omega square gamma by 8 0 0 gamma by 8. Then you have your angular velocity terms, and then there are the angular acceleration terms. So here gamma is a non-dimensional number and it's called the blade lock number, and it is given by rho c CL alpha r power 4 by I beta. So CL alpha is the lift curve slope for your main blade, and C is the chord length of the main blade, and R is the length of the main blade, and I beta is the same I beta that you have been seeing. It's the moment of inertia about the flap hinge, and this is the blade lock number. So the reason why this number is important is because this number kind of represents the ratio of aerodynamic force to inertial forces, and you can see that it is responsible for coupling in by with respect to the angular velocity, and I think something is, yeah. So if you want the equation for forcing function, what you need to do is you need to express your Fz, which is the force at that elemental location previously which I showed you, as a function of the angular velocity of the vehicle, the translational velocity, and the blade flap angle. And once you express it like that, you can perform the integration once you express it like that, and then you will get something like this. And also it will be a function of the control input, the blade pitch angle at the two azimuthal locations, the x and y directions. Okay. So if you discard the high frequency dynamics, so discarding the high frequency dynamics, when I said previously, what I meant was that discarding the advancing mode, so just ignore this part which includes the p dot and q dot term, and also a double dot terms, so that I have erased. So if you do that, you will get this equation, this new first order equations for your tip path plane, and comes out to be 16 by gamma omega a dot minus a minus 16 by gamma omega q plus p by omega 8 by gamma omega square k beta by I beta times b plus theta a. So similarly for the longitudinal direction, gamma omega minus b minus 16 by gamma omega p minus q by omega minus 8 by gamma omega square k beta by I beta 2a plus theta b. So you can so this 16 by gamma omega is your main rotor time constant. And I am going to denote it by tau m, and that is 16 by gamma omega. Okay, so this is a first order ODE, and the time constant associated with this first order ODE is 16 by gamma omega. Again, gamma is coming here. So what it says is that if you have a system, if you have a helicopter with a large gamma, your time constant is much lesser. And also if you operate your helicopter at a larger angular velocity, if you rotate the rotor at a higher velocity, your time constant of the rotor comes down. And if you write it down in a matrix form, or so eventually, and again theta A and theta B are the cyclic angles of the blade. So if I have my helicopter, this is my tail direction, fuselage, and so this is my body frame y axis, this is my body frame x axis. So theta A is defined here, theta B is defined here, and your B is defined here and A is defined here. So A is the flap angle at this location, at this azimuthal location, and theta B is the blade pitch angle at this azimuthal location. And theta A is the blade pitch angle at this azimuthal location, and B is the flap angle at this location. Okay. I think I have made a mistake. I think it's the other way around. I'm sorry about that. No, once again it depends on the way the rotor is rotating. Okay. It's dependent on the direction of the rotation of the blade. So maybe I'll clarify this a little later. That's not very important. But all you need to know is that theta and theta B are the control inputs affecting angle A and angle B. So so if I write in terms of tau m, it would so this would, it can be written as A dot is minus 1 by tau m A and minus small k beta by 2 omega I beta B minus omega y plus 1 by tau m theta A minus omega x by omega, and B dot is 1 minus 1 by tau m times of B plus k beta by 2 omega I beta times of A minus omega x plus 1 by tau m theta B plus omega y by capital omega. So what this equation essentially tells us is that, so this can be considered as a rotor tip path plane equation, the final form of the rotor tip path plane equation. So what it says is that if I just ignore the remaining terms, just if I consider this term, this is a first order system and it is stable, and so these terms are responsible for adding the cross coupling between A and B, and this omega y and omega x are responsible for introducing damping in the system. I'll try to show you a plot wherein if I have my helicopter, initially at t equal to 0, if I give a large angular velocity to this fuselage, what happens is that let us say this is my angular velocity about x axis and this is time. So this would, let us say this is like 360 or maybe 2 pi radians per second, this particular value. If I initialize my omega x as this, it would damp down to 0 in almost like 1 second for this for the helicopter, for the small scale helicopter that we have seen previously, like the one which we have seen in the video. So that is the kind of damping that is there in this system, I mean with the kind of numbers associated with these parameters. So and that is coming because of the presence of this omega y and omega x, and the cross terms due to the angular velocity can be easily cancelled because we can precisely measure the very accurately measure the rotor angular velocity omega, capital omega. So this can be easily removed by means of feedback. Which point? The removal of the cross coupling, the damping. I'll show you the plot because this is just a rough drawing.
No, no, what did you start with and what happened next?
So if you give a large angular velocity, so this is my helicopter and this is my body frame x-axis. If I give it a large angular velocity,
You come and externally give it a large
I'll come and externally give it a large angular velocity. Let's say it's like 360 degrees per second at t equal to 0. It will damp down to 0 the angular velocity in less than a second, almost a second's time, for the small scale helicopters that we see. So that indicates the presence of large damping in the system.
But how are you relating that to this equation? That equation?
Uh, well, it's not, you cannot completely infer that from this equation. You need the fuselage equation also, because this omega n x and omega y are associated with the fuselage, okay, and then there is a interaction between the fuselage and the rotor by means of this spring stiffness root k beta, okay. So you cannot directly infer it from here. So I'll write down the fuselage equation and I'll collectively write down the equation of motion for the rotor and fuselage, and then also you won't be able to see it directly, but if you simulate it you will find this kind of behavior in all three axes, okay.
How does this play to our advantage? It will reject disturbance externally very fast.
Yes, it is, in some sense it is good thing, but if you want very large angular velocity motion, then what it would mean is that if you are trying to design a controller for this helicopter, you have to cancel this omega x and omega y, right?
You have to induce the omega x and omega y.
No, no, this is the term which is causing the damping, right?
But for a maneuver, we want the fuselage to move in a certain way, right?
Right.
So we want a certain function for omega y.
Yeah, so it may not be exactly like this, right? So this is the one which is causing trouble. So we would like to remove this term, okay, and in doing so we have to know precisely this time constants tau m, and if you know precisely exactly this value tau m, you can cancel omega x and omega y. But the problem is when you don't know exactly what this tau m is. Let's say there are cases when you, let's say you have an overestimate of tau m. In that case, if you try to cancel this omega y, you may actually introduce plus omega y in here, and that is like introducing positive damping in the system. So it's like you are introducing, making your system more unstable, okay.
So you are saying by designing theta we want to cancel omega y and omega x from these equations.
Yeah, yeah. If you want like very fast maneuver and all, you don't want these terms, because this is going to damp, it's going to drain the energy out of your system. You can look at it like that. There are other ways of looking at it also. So, so this was the rotor tip path plane equation. Now I'll write down the equation of equation for the fuselage, which is nothing but the Euler equation for the rigid body, and then we will try to see how this equation is going to couple with this equation of the fuselage. So, so the fuselage is modeled as a rigid body. I am a fuselage, and here is my main rotor shaft, and let's say this is my hub plane, and my rotor tip path plane looks something like this. This is my rotor tip path plane, and it is tilted at an angle of beta 1s, which I am going to denote it by B. So there is my root stiffness spring. Because of the tilting of this rotor like this, my thrust vector is also tilted. This is my thrust vector, and my center of mass for the fuselage is somewhere here. This is my center of mass, and the distance of the center of mass to the hub is h. and because of this, so there are two sources of moment because of this rotor on this fuselage. One is due to the tilting of the thrust vector and the other one is due to the spring, okay, and because of the deflection of this thing. So there will be another moment acting on the fuselage. So the component due to the tilting of the thrust, I will write it as mt, and that is your h. So what is that? So it is this distance. This is h. So if this is b, so is this, and this is h. So this is h sin b, okay. And when b is small, h sin b is hb, okay. So this is hb into this force, which is T, and you have also the moment due to the spring. So this is k beta, spring stiffness is k beta, and that is simply k beta into, so I will denote it by k, that is k into beta. So beta at this location, azimuthal location, is beta 1s, which I am calling b. So the total moment acting on this fuselage due to this rotor is this plus this, and that is, so about the x axis, that would be k beta plus ht times of b, and about the y axis it would be k beta plus ht times of a, and this k beta plus ht can be called, I mean I am calling it as the equivalent spring stiffness, and that is denoted as this is denoted as capital K beta, okay. So here is my the moment about the x axis and moment about the y axis. What about the moment about the z axis? So for small scale helicopters, that can be approximated as a first order system because of not just because of the rotor, but also because of the servo dynamics. So I can directly write my the moment about the z axis to be, well, its dynamics to be mz dot is minus mz by tau t, where tau t is the time constant for the tail rotor, plus capital Kt theta t by tau t, okay. So if I combine, so if I multiply this equation, the rotor equation, with equivalent spring constant k beta, then I will have everything in terms of wherever I have a, that will become my, and wherever I have b, that will become mx, okay. And then everything can be written in terms of mx dot is something and my dot is something, and you can write the whole thing as m dot is a m minus capital K omega x y plus capital K a tau into theta, where your capital M is the vector of all the moments mx, my, mz, and A matrix is given by minus 1 by tau m k 0 minus k minus 1 by tau m 0 0 0 minus 1 by tau t. And A tau is given as one by tau m. It's a diagonal matrix. And your capital K in that equation is the stiffness matrix K beta, K beta, K tau. These are all capital K, KT. Okay. And omega xy is just the vector of angular velocity about x and y, ignoring the angular velocity about z axis. I'm sorry, this has to be 0, right? And this k, small k, is small k beta by 2 omega I beta. And my theta is a new control input, and I am just denoting it as theta b plus omega y by omega, theta a minus omega x by omega, and theta t. This is my control input to the system. So I have a equation for the moment acting on the fuselage, first order dynamics equation, and that moment equation has got terms from terms like angular velocity of the fuselage, and the fuselage equation is simply the rigid body equation. So the kinematics would be r dot is r omega hat, and j omega dot plus omega cross j omega is m. So m is the moment acting on the fuselage, and omega is the angular velocity of the fuselage, and r is the rotation matrix representing the orientation of the fuselage with respect to an inertial frame. Okay. And this is the kinematics and dynamics, and then you have the moment equation finally. M dot is coming from there. Am minus k omega xy plus k a tau into theta. So this is your reduced order equation for the helicopter, small scale helicopter.
Omega and omega xy can be related by a linear transformation, right?
Yeah, it's not invertible.
Not invertible.
Hmm.
Identity with the third element zero.
Yeah.
So why don't you write it that way here?
Which way? Oh, you mean you want
Why
to?
don't you replace omega xy by some matrix into omega? Because omega is what we want finally.
No, I don't want omega. Why do
We
I?
want to control the fuselage, right?
Right.
So if we are dealing everywhere in omega, then won't that be more beneficial?
I don't think it's going to be a big problem if you put it like this. I did not find any difficulty. This is fine. So maybe I can show you the plot of the angular velocity decaying with time. You can see the angular velocity. So this is omega x and omega y, and I guess I have started at 2 pi radians per second, and then it decayed to 0 in less than a second, well less than a second. I mean, I guess I would say that it's decayed to 0 in 0.4 seconds or so. and that's the kind of damping that is there in the system because of the presence of omega x and omega y in the moment equation. And the damping moment generated, you can see that it's about 17 Newton meter, and that's very significant for a small size helicopter. So that is what I wanted to show you. So the reason why I have perturbation in y because of x is because of the cross coupling that is there in the moment equation. So that's primarily because of the cross terms in A. Yeah, these terms. So this k term is responsible for coupling the A and the moment in x and y direction, and also because of the angular velocity coupling. So this omega x and omega y, you see, A is primarily affecting omega y, but there is omega x also coming in, and you have B. So these are the two cross coupling terms which are there in these equations, and that is why when you have a motion in one direction, it automatically excites the other. Any questions?
MT is negligible with this comparison to the other one, right?
Which one?
There are two moments, one because of the spring and one because of the
Yes,
lever arm.
right. So the moment due to the thrust vectoring is negligible when compared to the thrust the moment due to the deflection of the rotor. Yeah, that is also there. I forgot to mention that.